Welcome to a new test and teardown video. This time it's a data technology model 40 4.5 digit digital multimeter. I believe the readouts, well, it's difficult to see, right? But this has to be Beckman neon 7-segment display, so they are high voltage gas filled. That was exactly why I got this one at the local flea market, because I just find these kind of cool displays interesting. This also reveals a little bit about the age, or the possible age. So about 1970, 1960, 1970, in that range. There is not a lot to say about this, really. I couldn't Google anything at all. So if you happen to have manuals, schematics, or anything lying around, could you please scan this and put it online and tell me about it? I definitely would love to get some information about this unit. I found an eBay ad selling a manual for $20, but that is definitely not going to happen. I hope there is a special place in hell for people doing this. If you want to go to heaven, what you need to do is scan it and put it online for free. Thank you very much. With love and all good things. So there's a little handle here on the side, and it is sticky, nasty. So I will have to clean this a little bit more. There's a little logo here on the side, DT. Look at that. Can we find any other? Yeah, we got a little sticker right here. Oh, look at that. 1973. So I was a little bit wrong with my guess. And what have we got here? Model 40. Got some serial numbers, part number, and all that kind of stuff. It also says this company is from Santa Ana, California. That is a nice place, by the way. I think we should try and open this thing and have a little look. First, I am a little bit curious about what is this. So there was a hidden compartment. When I pulled this a little bit harder, a little loose fuse, and some sort of an expansion port. Wow, interesting. And we even have a main voltage selector. And here it just says, no, they forgot to tick this, right? Why didn't they just say voltage settings behind the lid here? What is the point? Well, let's try and look a little bit inside this fantastic unit. So it's a 2-layer circuit board, and it's really beautiful. This nice order of everything. And look at the trimmers here. We say 10 volt, 100 volt, 1 kilovolt, 1 AC. Yeah, everything is nicely explained. I'm of course a little bit worried about those capacitors. They are mounted right next to the diodes and voltage regulators. So this is of course the warmest place to be. So this will eat up the lifetime of those capacitors. In this corner here, I don't know if this is easy to see, -1 volt and minus or plus 1 volt. We've also got a test point for -10, and down here, I don't know if that is easy to see, but there's a plus 10 volt test point as well. So I believe what we have here is the voltage references, and that is something I need to inspect more carefully. I think the type of converter here is a ramp. So what they're doing is, we got some timers. Probably I can show you a little bit better like that. See? All those gates, okay? Then we got a little flip-flop and some more gates. And here we got all the counters, the 7490, that 4-bit counters, decimal counters, each of these, right? And then we got some latches and 7-segment high voltage drivers for the Beckman displays. So at least that is the way that I think it goes. I think the display here is a little in a socket, so I can pull this out and clean it. But I don't see any reason for not powering this up. Let's inspect the bottom side. Definitely a manual hand-drawn layout. See, they figured out, oops, we're too close to the screw, so we add a little plastic isolator instead of just doing it right. I mean, you could easily have made a little bit more room and just, this is just so typical. See, start to make room and then, oops, I don't need the room. And then you don't, use it for something else. Got good shield connection to the top and the bottom, because the rest is of course plastic, and you need a little shield here. Inside the lid I find this information here. So this is the calibration chart. So I think I will go through it in this order to measure all the different things here and calibrate this and calibrate that. They even just call it these things instead of having a more fixed reference to a trimmer number or something like that. I was just about ready to try and power this thing up, but I tried different connectors and they just don't fit. I mean, this looks like a normal IEC socket, right? But you know what? We got these annoying little things here that makes it impossible to go all the way in. So I will have to modify this one. And if I take an angle one, it's probably even worse. See? Nothing happens here. This is not gonna work. How stupid is this design? Why would you do it like this? So, after a little bit of snitzen here, yeah, then we are all the way. Easy, mate. Wow, that is a beautiful. Holy moly, that is nice. It looks like it's a little bit out of focus, and I believe I need to just clean the acrylic here. Let me try and focus on this. Ooh, this is not so good. If I focus somewhere else, yeah, okay. I'll definitely try and clean it up. So what are we in here? DC volts, 100 volts, so I can just give it like 18. What? Is it that accurate? I did not expect it to be that accurate. What the heck is going on? So what is the next range? That is 10. Whoa. And what if I go? And then I get another digit. Oh, this is so lovely. It is that accurate. And I just turned it on. I will, of course, have to check out the temperature drifts and all that. So it's using 8.4 watts from mains at the moment. And I did crank down mains voltage to 220 because I wanted to measure what is going on down here. And I will, of course, check the capacitors and all that. But there's no definitely no ripple or anything triggering it. So this is 10. Let's try and give it a little bit more and see what happens in... Ooh, it can't go. That is a little bit odd, isn't it? So we are in the 10 volt range and it shows 11. So let's give it 12 and let's see where is the... And then it says over at 20. Okay. That is a little bit weird, isn't it? So why are we having a 10 volt range, but it should have been 20, right? Okay, so let's go the other way around and see if it's completely symmetric. And that seems to be the case as well. Oi, oi, oi. I am very, very happy. This was a good trip to the flea market. And if I short the inputs, we can of course go all the way to 100 millivolts and it should be 0. And let's try and give it 100 millivolts. Find 100 like that, and we will see this is open, it's just full on noise like that, and this is 100 millivolts. I will have to double check what it is in fact, because this is where my power supply is not super accurate, by the way. So this could easily be my own power supply. So we are back. I powered up my other little meter here. So let's see if we can remember this. 101.8 something, right? 101 point, very close to 8 something. What the heck? Toodaloo. I think it's gonna be nice and sharp, my picture now. And I was right about Beckman. So the right display is the standard Beckman SP352. But the other one is a sperry. So I don't know who is copying who here, but normally I just call these Beckmans. But they're exactly the same. And here they are just side by side. And of course you can't see any difference at all. I really, really love those types of displays. Because it's gas-filled neon, high voltage, and it's a little bit like Nixie, but not exactly a Nixie. Yeah, I try to clean them as much as I can, and now I will just try and plug it in and see if I get a nice, good picture. I think that helped a lot. Why is it like that on the one? But the thing is that I think the camera behaves a lot different to the dynamic range or the sharpness or something like that. With my eyes, this looks super, super sharp and nice, and they all look like exactly the same intensity. And I don't see any blink or any annoying things. I think this is direct driven, so that is a really, really nice. So here is what I've done. I went into the most holy of the area right here. So we got a couple of op amps, some field effect transistors, and we got a little oscillator here. So the oscillator is running at 138 kilohertz. And we got a capacitor here that is charged and discharged with the input voltage, whatever voltage we want to measure. And this is called a dual slope AD converter. The only thing that kind of sets what is the resolution of this type of converter, that is how fast you want to clock, how long can you count, I mean how many bits of counting. But if you count really, really, really fast, you can get a super, super high resolution. Obviously you also need very, very stable components and very fast pulses to control the charge and discharge and analog input circuits and stuff like that here. But so this is my capacitor. This is a polycarbonate capacitor, so it's insanely stable over aging and temperature and all that kind of stuff. And here is a tiny little pulse for the reset when time is up. When there's a compare match, then you of course reset, and then you go the other way around, discharge the capacitor, and then you're ready for the next round. So this is the counting time. How long are we counting? And in all that time, we can see the different counters getting different clocks. I measured here on this that will be the counters, the ones and the tens and the hundreds and so on, right? So obviously we get a higher and higher frequency the more to the right we go, obviously on the clock here, right? And so let's look at the scope pictures. Here is the display now says 10,000, that is 10 volts. And we see this tiny little reset pulse here. And this is of course the counting time here. And all this is the reset. Okay, so let's try and change the range to 100. See? The discharge time is the same. And here is the measurement. The charge time is now a very, very short pulse, because now the AD converter sees a very low voltage, and this is of course the counting time is very little, and we count only 1000, that is 10.00 on the readout. If I go further up, so this is 1000 volt range, obviously I count only 100, and it says 10.0 volts on the display. And in this case, the counting time here is very, very small, right? And you can't even see anything here. So now I've changed the trigger system, so I trigger on the count time right here, and I have added a readout right there. So now we see this is I am now in the 1000 volt range, and I have 10 volts of input. And look at that, it says 740 microseconds. Okay, so let's try and change the attenuator or the input like that. So now we are in the 100 volt range, and we read 1000 counts. Look at that, the time is now 7.4 milliseconds. And can you guess what is going to happen if I go to the 10 volt range? Let me dial a little bit here. Then I get 74 milliseconds of count. So it's exactly a factor of 10 up all the time. And of course my readout is exactly a factor of 10 more every time I move around. The range is like that. So this is how a dual slope converter works. I think it's always interesting to play a little bit with the different ranges as well. So now I am in AC voltage, 1 volt, and my input is of course 1 volt RMS, and this is a 10 hertz input. Let's go all the way down to 5 hertz, and then it will of course jump and jitter a lot, but you can still read, I mean 1.0. So let's try and crank up the frequency quite a lot. So here is 100 hertz, and then it is of course pretty stable. 1 kilohertz is that. And let's just try and all the way to 10 kilohertz. I said 20, yes. 30. How about that, huh? 40, and then, okay. So it's super duper accurate. I mean, all the way to 30 kilohertz. Amazing. So let's look a little bit at the resistance measurement. I mean, it's really funny when it's open. It just goes random blinky blinky something. So at least this is how you know. And here is your 0 in 1 kilo ohm range. So let's just grab a random 1 kilo ohm 1% metal film resistor. And here it reads 1003 sort of, right? How about we take the wires here, including our resistor, and let's just plug it into another random instrument I just happen to have right here. And I am now also in 2-wire resistance. And what do you know? Isn't it more or less the same number? Of course, we also want to play with the last funny range. So here is a resistor. It's supposed to be 10 mega ohms, right? So this is the 10 mega ohms times whatever it says here. So that means if this is in 1, then I read 10 mega ohms. So 10.1617 something, right? Again, we can take the, oops, let's see what happens here. Oh, this is of course hum. So you cannot touch the wires when you're measuring high resistors like this, or you have to put it down and leave it completely alone. And here you go, your 10.16 mega ohms. I think I found a range where it just don't work. Here is a 100 mega ohm. Whoa, difficult to. Can you please do that? No, you cannot. But it says 100 mega ohm, and I don't want to touch anything. So, shouldn't it be like that, right? No luck. What if I crank up? No luck. I don't know what's going on here. So is my resistor not working? Hello? Is that really what we have? No, that is not what we have. My resistor is working. So that is that's what we figured out here. So the maximum range is 10 mega ohm. And this is probably written in the manual if I only have the manual, but that is just a known limitation. All right, now I can clean up everything. It's just one little tiny detail to show you. I, of course, did change the power supply capacitors. I drilled a little bit of hole around here because I think they run a little bit nice and warm in this area here. See, with a little bit of holes here, I think that maybe a little bit of air can move around. I also added a few tiny holes here and here. I mean, not a lot like that, but you can see some holes here on each side. I mean, just so it's moving a little bit. Because I am so happy about this unit, and I want it to last the next 40 years. Oh, 50 years. Are you crazy, man? Is 50 years old? All right. Thank you very much for watching. I hope you had a little bit of fun. See you real soon, okay? Bye-bye.